Okay, if you're going to do the U-try calculation, you might want to try it on your own before watching the remainder of this video. The main thing that's different that we really haven't talked about is part D. So if you want to fast forward and just listen to that section, you might want to do that as well. All right, as we take a look then, we are going to be actually calculating the Gibbs free energy for the entirety of the reaction. Notice the downfall to that second equation, and I want to use the second equation because of my temperature. So the downfall of this second equation is very simply the fact that it's easy if you have delta H and delta S already calculated. As you see from this example, we're actually going to need to calculate each one first. So let's begin by just balancing our reaction. And it looks like we can have a 2 in front of the lithium hydroxide and a 1 in front of the Li2CO3. It also looks like we can put a 1 in front of CO2. That gives us 4 total oxygens on this side, so a 1 in front of water. That gives us 4 total oxygens. And if we just double check, there's 2 hydrogens on both sides. All right, again, try to get those to be nice whole numbers. So lowest whole numbers for your balancing. Because again, since you are using the coefficients in your calculations, having different coefficients will change your answer. So we calculate the change in enthalpy. Since we want to calculate for this, the easiest thing to select from is going to be using heats of formation. So we have our table, and we're going to find the formation. Let me actually start out with the coefficients. So 1 times the formation of lithium carbonate. And again, folks, you do not have to show all of this, but this is for your benefit so that you can follow along. We've got the water as a liquid. So 1 times that formation. And then our reactants, remember, are over in the next part, so we're going to subtract formation of CO2 and also 2 heats of formation of LiOH. All right. Now again, you're going to pull out your thermodynamic data table, and I'm going to try to remember some of these values as we go. Again, the big thing to remember, let me just flip over to it. The big thing to remember is that as you do this calculation, you pay attention to which column are you in fact pulling from. That's going to be probably not necessarily the most challenging, but the thing that you just want to watch out for because there are a lot of digits here. So as we calculate, right, use your heat of formation table. We have our lithium carbonate. We've got a negative 1215.6. And we're going to add the water. And again, remember, water is the liquid form. So we're going to add a negative 285.8. And then subtract the whole quantity. You want to, again, get the carbon dioxide. So that's a negative 393. Whoops. That's a negative 393.5. There's only one of those. And then we're going to add 2 of our lithium hydroxides, which is a negative 47.2. And again, notice how these are being, most of the values are going to be negative, very simply because you're forming, and forming bonds ends up being exothermic. All right, so as you wrap up on your calculation, again, We've canceled out the moles, so a negative 133.5 kilojoules is your answer for enthalpy. All right. For entropy, we're going to end up doing the same thing. So again, using your reaction, we'll go ahead and get the entropy, right, the absolute entropy of lithium carbonate. And you can see now, as you get more comfortable with this, I feel like a lot of you might want to skip this first step and just kind of jump ahead to filling in the variables. That's totally understandable. So if you want to do that, no problem. Again, just watch your signs, and of course make sure that you are in fact collecting the information from the correct table column. All right, so we're pulling from the second column now of values. And so again, we're going to look up the lithium carbonate with a 0.0904. We're going to get the water as a liquid with a 0.0699. We want the carbon dioxide, and that's going to be 0.2136. And again, 2 of the lithium hydroxides, so 0.0502. All right. Again, as you calculate this, you have, in fact, removed the moles by multiplying by each of the coefficients. But at the same time, because it's entropy, keep in mind that what you do have present still is the Kelvin in the denominator. So I right now have a negative 0.3077. I'm going to go to 4 decimal places because all of these are going to 4 decimal places. And again, the units are kilojoules per Kelvin. All right, so you can see then that we have 2 processes that we're looking at. One is the heat, which is nice and exothermic. It's going to release a bit of heat into the environment. The second one is the chaos, and it's a negative value, so we are becoming less disordered and more organized. And I know that because the negative value tells me that we're losing our disorder. All right. Finally, we're going to calculate our delta G using the equation where we plug in the heat, and we're going to go ahead and take our 1000 Kelvin and multiply by our entropy. So again, a pretty easy calculation, just making sure that you end up placing it in the correct location. So I have the wrong entropy. Hold on, what did I do wrong? Oh, yeah, I totally calculated it wrong. Although I'm also not getting the same value that I listed. I'm getting, sorry. Um, 1546, so 0.1546. So a slightly different answer than was listed. And now using the Gibbs free energy equation, I'm getting a positive 21.1. And again, that's going to be in kilojoules. So since it is positive, remember that means non-spontaneous. All right. So for the last question, at what temperature will the reaction just become spontaneous? This is an interesting question. If you know that delta G, when it's negative, it's going to be spontaneous, but when it is positive, it's not going to be spontaneous, then what value is where it switches? If you're thinking like math or graphing, hopefully you thought of the number 0. So it turns out that if you want the reaction to switch in spontaneity, you calculate the temperature at which delta G will be 0. So we're going to assume that delta G is 0. Obviously it's not. But we're going to plug that in and then also plug in our heat. We'll solve for the temperature and plug in our entropy. So again, this will give us the value of delta G when delta G changes from spontaneous to non-spontaneous. It's also going to give us the delta G as it's changing in temperature. So that's one thing that's unusual. There are 2 different equations for delta G because delta G is highly impacted by changes in temperature. For this calculation then, again, it's just a matter of plugging in and calculating. And I have, with these slightly different numbers, I have 864 Kelvin.